So next up, we have Igor Luppi. I'm going to butcher the names, right? Igor Luppi, Bruno Moura. Moura? Yeah.
So if you guys want this timer. Oh, okay. To swap the slides, should I just use the computer here? Sure. Oh, okay. Oh, okay. Let me just perform a quick sound test. Can you guys hear me from here? Yeah, yeah. Can you guys see me from here? I know. Okay. Oh, good morning, everyone. My name is Bruno. I work as a flight software engineer at Visiona space company, which is a Brazilian space company. And I'm here today with my coworker Igor to talk to you guys about VCUB1, the first Brazilian satellite powered by the core flight system. This presentation tends to be a way more general case description of utilization of the framework in a mission mainly controlled by its onboard computer running cFS. First, talking about some of the mission objectives. Basically, we had the intent to validate our onboard software, both related to OBDH and AOCS modules, and generally perform our payload activation control. Those being our software-defined radio, our SDR payload, and our image collection equipment, our optical payload, which is a 3U camera. And brief spoilers right here. Some of the mission success already accomplished by the mission were we were in fact able to perform Earth imaging. We will talk a bit more of this later. Data collection over Brazilian territory using our SDR payload. Our general OBDH validation was correctly performed through mission operations scripts and supports. And the AOCS software was already validated by maintaining the satellite in a safe power positive state. But there is a caveat. The AOCS software still has to validate some of its fine pointing modes for critical and precise operation. Here is a macro representation of some of the satellite's operational procedures performed and, so to say, operational features as well. Some of both its UHF and solar panels deployed. It's both SDR, IoT, and imaging mission control and payload activation. And for example, its 3-axis stabilization control performed by its auxiliary onboard computer. Here's a brief description of the OBDH team. Here we have Nicholas, which is our OBDH team coordinator. Me and Igor here presenting to you guys as OBDH engineers. And finally, Hanufo and Davi as AOCS flight software engineers. Shout out to those guys who are watching, probably. Well, talking about our system engineering process. The satellite was basically developed in compliance with ECSS, which means it was tailored as a standard for small satellites. And we talk it in that way because of the less risky operation or criticality of the satellites when compared to more critical missions or even tripulated missions. That's why they were tailored. This way, in the system engineering process, we end up performing requirement definition, followed by component specification, then assembly and integration, and finally testing for all of our subsystems. And here at the right side of the presentation, you guys can see a couple pictures. The top and bottom one are pictures performed in, I don't know how to say it in English, clean room, I want to say it, in the AIT phase of the satellite. And the middle picture is a split vision of the VCUB in its mating phase. In this phase, we were able to correctly put out the camera and couple it with the rest of the satellite, which is what you guys are seeing here. Now, talking about our NASA wannabe ground control system. Here are some of its descriptions and general devices, so to say. First, we have our real-time telemetry visualization engine, which I will be talking about shortly, our baseband control system, and all of our stations used respectively for mission planning, simulation environments, and general operational scripts. And lastly, but not least, our humble ground path indicator, which of course turns green whenever the satellite is passing over us. Here we have a deep look at our real-time telemetry visualization engine. As some of you guys can already know, we use Grafana, and we use it due to our ground software being composed of Cosmos. Cosmos, all of you guys may know Cosmos. And as soon as real-time telemetry reaches our Cosmos interface, this telemetry is also put in our database, which is then processed and shown in Grafana. This generates a pseudo, almost let's call it software real-time telemetry visualization due to those 1 or 2 seconds of insertion in the database and data visualization. Just to give some examples of the data presented here, as you guys may know, we simply map our main telemetry packets in our tables, then we can show certain data of those tables in our telemetry visualization. At the top of the panel, you guys can see, for example, the satellite mode. At both sides, you can guys see which channels are powered off and on of each of the subsystems which deal with alimentation, as well as at the bottom, some CPU and memory usage status, and depth of discharge of the battery, and of course, since this is a presentation about cFS, some cFS event software and initial software running on the background. Okay, talking about some of the operational challenges faced by the team throughout the operation of the satellite. First, the main challenge which we were presented to was the identification of the mission, because it took up to 2 days for the operation team to correctly match the TLE orbital elements with the antenna TLE, so we could get good link usage with the satellite, followed by the optimization we had to perform on daily procedures, which had to be tailored to match correct space conditions in our scripts, which eventually we did not consider in our initial implementations. And lastly, but not least, the automatism that we had to achieve to ensure that the satellite would be alive in the next passage over the antenna, which was one of the most critical parts. But at the end, we believe that we reached a so to say, flexible and safe development and operation environment in which we can perform any procedures at any given time in many different ways, just to encompass any possible operational challenge that we face in a daily basis. And here are some pictures of our humble ground system and events that happened throughout the company during this process. And now getting to the good stuff of the satellites, here are some image examples taken by the satellites, respectively images from Espírito Santo, Brazil, Yushu, China, Phoenix in Arizona, if I'm not mistaken, in the US, and Milan in Italy. Those images are here present just to show, just to in fact exemplificate the capability of the satellite, but they are present here in different steps of our image processing tool. That's why the last image, for example, is in some sort of grayscale. Also, it's worth mentioning that all of these images were taken without proper camera calibration, which means that the image quality can be even further enhanced. Now, why use cFS in such a first-timer mission? Well, we actually need a portable and extendable software. And as you guys may know, cFS and software related to cFS do that in a great manner. We needed the software to be controlled by onboard device, onboard service, such as System D or correlated systems. And the software had to control multiple subsystems simultaneously. And of course, previous Visiona employees came into previous previous editions of this flight software workshop and saw people using cFS, and then they decided to embrace the idea, and we took cFS as our main software. And once again, describing briefly some of the things that we achieved by this, we could correctly test and deploy our software in both ARM and x86 architectures. We mostly use that by the PSP, the platform support package from the cFS core. We also wrote a custom COM driver inside IOLib for inter-subsystem communication. And of course, we developed various applications for custom mission needs. And since this is an cFS application, this is a kind of our lollipop diagram, as we saw previously in this event. The right side of the presentation contains hardware-related stuff just for representation and clarification, but our focus here will be on the left side of the presentation, which contains our onboard software architecture. Here, the marked boxes are the modules inside cFS that were either modified to fit our mission's needs or built from the ground up, including payload applications, some mission-specific applications, and of course, as I described, the PSP layer at cFS. This way, talking about some of the operational features available by the VCUB, we will present them and iterate over them more deeply as the presentation goes on. First, we have our onboard automatic mode management, which turned out to be crucial due to to the automatisms of the satellite, our region-based command execution engine, general attitude control and payload activation, health check and FDIR control, and finally, application and framework level software updates along with our our duplex file transfer engine using CFDP. Now, taking a more technical deep dive in the aspects denoted, the automatic mode management engine was, as most of you guys may imagine now, it was a custom application developed by the team at Visiona, and it works basically by checking telemetry packages, and upon meeting certain conditions, it reports events and reporting that the mode change was in fact changed, and as well triggering execution of stored command tables to perform operations upon those mode changes. Also, it has a strict relation with the scheduler application, so that along with the mode changes itself, it can also change the data rate, the telemetry rate generations, as well as a data pooling requests from the equipment. Now, secondly, but lastly, regarding the topic that I will be presenting here for you guys, is our region-based command execution engine. And of course, as well as the mode change engine, it was implemented in a cFS application. It basically uses regions as geometric definitions of a list of coordinates, which we'll be talking in the next slide. But at the framework level, those regions are simply cFS tables. The application then checks those tables with real GPS telemetry data generated by the OCS computer, and then sends triggers, which are in fact telemetries, upon entering or leaving a given region. And also, just for configurability and such, those regions may be enabled, disabled, or configured by commands. Given a brief example of a representation of a real image used in VCUB operation, at the right side, we have a pseudo software-like representation of the region as a mentioned list of coordinates, and at the left side, we have a region of Brazil. In an example of trajectory from the satellite coming from south to north in the image, upon entering the region, it could be configured, for example, to start to set up an image acquisition, let's say over São Paulo, and performing it. And upon leaving this region, another table would be triggered, which would then perform the cleanup of the previously set up procedure. This can be applied to SDR operation, camera operation, antenna deployment, any operational procedure that tends to be needed. And finally, once again, demonstrating the flexibility of the cFS framework, those regions, due to being represented as tables, they can be updated, generated, and uplinked to the satellites at any time, given any conditions of the operations and anything that would help the operation team to control the daily mission. Here, I end my part, and I'll hand it over to my coworker, Igor. Thank you.
Thanks, Bruno, for our excellent introduction and the insightful start you had. Good morning, everyone. My name is Igor. I'm happy to be here today. And as Bruno mentioned, I'm a flight software engineer at Visiona Space in Brazil. Now I'm going to dive into a few features and as well some validated procedures we have with the VCUB1 satellite. As you may know, the cFS has a power flexibility regarding child tests, for example, and in the context of attitude control, those child tests are some features that are important because we can read data and inject data into the control loop to do the next steps in the actuators, for example. Also, regarding the strategy we have for those applications, we have two different cFS applications, in which the first one we have as a driver-like abstraction hardware layer, where we can read and gather data from any place in our satellite. And the second one is the application that has the power to translate this data and do what is needs to be done in our operational mission. Also, as you may already know, regarding this flexibility, it's easy to reconfigure the satellite and its applications due to the cFS tables. Talking about health check and autonomous fault detection and isolation and recovery. We have this out of the shelf in the cFS because it already has some powerful features, and we can just modify and customize it to our needs in our mission. For example, when you talk about the general health check, we chose the HS, health and safety application, to be the main application to ensure the status, the mission mode, CPU monitor, memory, etc., is being covered by its application. And when we talk about FGIR itself, we have the limit checker application, which is also another powerful application that we customize it to be the application for our needs, for our mission. But it has, by its vanilla version, already powerful to manage those FG. And it can do telemetry, reading, masking, filter, and also execute commands to recover the satellite to a nominal condition. To give you an example for those who don't know, we have watch points and action points. Basically, the watch points are our, let's say, piece of information. They are labeled information that we can use to detect the fault, and they are used by the action points. So the action points are our rules. So they define how a FDIR is identified and fixed. And those action points use the watch points to check the satellite condition and status. We have done custom development under the watch points and action points to match our mission needs in this case. Now I want to talk about validated procedures. In the following slides, I'm going to show you real results we have, and this includes optimization of CPU, memory, software update, payload deployment and operation, image acquisition, image transmission, data collection, and attitude and payload refinement. Software update. Software update is something that we have done multiple times in a reliable and a safe way in our satellite. We have done like application update, configure files update, tables update, and even a firmware update. This one was pretty hard. The cFS has a flexibility in which it relies on the fact that it has shared objects instead of a monolith piece of software. So we can abuse this fact to optimize our software update strategy and update what needs to be updated and uplink what needs to be uplinked. So we can short what we need in terms of binary files to be updated. And this is pretty good because we optimize our bandwidth. Also, systemd services have been developed by our team to monitor and keep tracking of failure and backups regarding software update. And this is a pretty reliable way to do the software update. I'm going to show you in the next slides. Last but not least, CFTP has been proven to be a powerful tool to transfer files to the satellite. And this way we can ensure what we are doing whenever we do a software update. Well, this workflow is the software update workflow for VCUB1. First, we upload the files to the satellite. And then second, upon a software update trigger, we manage to do the backup of our current software. And this is done because we can get back to the current software automatically or by a manual trigger whenever we need. And once the software is updated with the new files, in this process, we start executing the new software, and the software becomes a software under observation. So if it proves to be a tough and reliable software after a period of time. We keep it as a new version, as a nominal version, and then the backup is archived. Otherwise, the new software is rejected and a backup is restored for the nominal satellite software. Thankfully, the last one has never been done. All of the updates have been successful. Interesting enough, it's really fast, the update. And the best part is we can split this process. We can do like the uplink in a pass or many passes we need. And then we just trigger the update whenever we want. We have done a lot of onboard optimizations. VCUB1 has just his first birthday, first year birthday launch in a few weeks ago, I'm sorry. And it has been a in-space laboratory due to the many optimizations we have done in this year. This includes optimization for CPU, memory, FD adjustment according to the needs of the mission, AOCS refinement, especially tuning parameters, payload performance update, SDR, camera, and also data collection platforms for the environmental data we have in Brazil. Now I'm going to show you a few real data we have in Grafana for our satellite. Here is two graphs that we performed a memory optimization in a software update. In the top, we have an application that uses to use in a linear behavior memory. So we identified that, and we were able to transform the linear behavior to a constant memory consumption behavior. It was a pretty nice enhancement for that application. It was done by a software update. We also updated and we reduced the control loop noise. We reduced the control loop noise, and this was a pretty good enhancement as well. And it relies in the parameters update that feeds the control loop itself. It was one of the main updates to help the success in the mission, the operation itself. Last but not least, here we have a graph showing the automatic thermal control loop operation of the optical payload. Based on a series of parameters configured by command, we can always ensure that the control loop maintains the temperature of each heater in the subsystem around a defined set point. In this case, we have a set point adjusted to 17 degrees Celsius in this image. It's necessary due to the thermoelastic focus adjustment system it has. It means that different temperatures set for each of its heaters result in different image quality due to the lens deformation. So you can see like how it stables in a certain set point. Well, let's look at some Visiona's key achievements. We demonstrated technical expertise in the satellite design. It was our first in-house satellite design. We managed the entire development lifecycle from the concept to in-flight operations. It's still operation. Today it's operating. The integrity effort resulted in a successful mission accomplished, and system validation reinforcement our commitment to delivering the results. Lessons learned. Finally, we had a reliable test environment. It's important to have a representative emulator and test equipment to avoid unexpected result on integration tests. Keep it simple. I do agree with the modern satellites income in the future, as we have seen today, and we must achieve that. But in terms of software engineer, we have to keep it. In terms of the software engineer, we must keep it simple. So we avoid boilerplate or bad patterns, things like that. And automatically CI/CD is really important because deploying in testing should be made as automated as possible because it minimizes human error in terms of software and everything. And also it accelerates the development and the deployment concluding, the picture we took just at the final testing of VCUB1, that was last year in the beginning of February. We are at Brazilian National Institute for Space Research, INPE. I'd like to conclude the presentation, certainly my gratitude to the VCUB1 team. And on behalf of the VCUB1 team, I'd like to thank you all. Now you're open for questions. Thanks.
Okay, so for a few questions, go ahead, Miles.
Yeah, I've got two small questions, if you don't mind. So the CAN bus with the IO lib, have you considered upstreaming that back to the NASA distribution of IO lib?
Oh, actually, we cannot get into the details of this implementation, so it will be private for now.
Okay. And then my second question is, do you have any examples of where the CI/CD pipeline was able to help you meet verification requirements for your, like at the project level, that you showed that CI/CD helped you meet requirements or check them easier?
Oh, actually, we don't have any examples here, but I can assure you it happened more times than I would like to assume. So yeah, we don't have examples, but it did happen.
Thank you.
Just to complement, in terms of CI/CD, we have like one facet that we can give you is the deployment process. We create a CI/CD to deploy the software, so we can easily, when the test phase, deploy new software whenever we need. Because, you know, when compiling to different architectures and different boards, you may like have a misconfiguration and choose the wrong board. So it's important to, at least in the deployment, you have to do this automatically. But this is one of few examples I could give to you.
So from online, can you talk about what you were using for your backend GSW database?
For what, sorry?
Backend GSW database?
Oh, ground software database. Oh, yeah. I'm sorry, I can get into the details as well.
Okay, that's an easy one then.
Yeah.
So do the attitude control loops run in a cFS application or in separate?
That I can say no.
Okay.
The control loops itself does not roll in cFS. The AOCS computer is a separate computer from the onboard computer in which cFS runs, and we communicate it through serial bus.
Okay, and I didn't see if your graphic showed this. How fast are software updates? Can you speak to that?
The software update can do under 4 to 5 minutes. It depends mostly of the size of the binary, but if you do the process in different passes, you can then trigger the software update in less than 4 minutes. You have your satellite updated.
How big was that software update? You said 4 to 5 minutes.
Oh, it actually depends.
It
depends on the size of the binary that are uplinked to the satellite as well.
Yeah, this is the default timeline.
Yeah.
Okay. I guess I was asking how big was that binary for the data?
How big? Oh,
for the time you just
I don't have the information right here,
Okay.
but
Yeah.
it varies based on the application that we were updating.
Yeah.
Okay, fair enough.
So I think
Are you also using stored commands app in conjunction with the LC app for FDIR responses and actions?
We do have shown the stored command application, and we use it. It's in our architecture.
yeah.
Okay. What are your overall thoughts on the way cFS recommends you handle FDIR?
Thoughts about FDR? You have to take care because it brings you the powerful to do the FDR, but it's not as easy as you think at first, because you have to define the state machine for your FDIR and then implement it under the umbrella of the applications the cFS provides. That's the hard part, because you have like a vanilla open framework, open with the application, and you have to define those machine states to really perform what needs to be done for FDIR. But you have the recipe, but you need to feel it, you know.
Igor and Bruno, great presentation. I will just say there's many more great questions online. Please respond to those, but I have to cut us.
To answer them after lunch.
Yeah, I have to cut us there. Thank you.
Thank you.